Hey everybody. So what we're going to do a little bit today is we're going to talk about the engineering by design process. Now, just like inquiry, there are a lot of different methods for this, and there's a lot of different ways to think about it. So I'm going to go over just a handful of them, kind of give you a general, a broad overview of what engineering by design is, and talk a little bit about what we can do to help our students learn to think critically, and as well as what are some different popular options you might have available for you. So we're going to go ahead kind of get started with the engineering by design or engineering design process. Now, what's important is that first we kind of need to understand what is an engineer, and that's basically a person who's trained, skilled, design, construction, use of a system or machine. When we think of engineers, it's not just science and it's not just math, but it's also language arts. They need to be able to communicate what it is that they do and what it is that they're creating to everyone. So there needs to be those communications, those language arts skills involved. Now, there's a lot of different type of engineering fields that are out there: mechanical, electrical, biomedical, chemical, civil, computer, nuclear, aerospace, industrial is not on there. So there's a lot of different types of engineers out there. Now, when we think about engineering by design, kind of describe what engineer, but by design, what does design mean? Well, it's a generic term. It basically means that we have to put forward some type of conscious human effort into how it goes and how it operates. So it's used in a way. So what are we doing to systematically solve a problem? So it's by design. How do we do this? So the process, if you think back to design, is a systematic process. So the design process, systematic problem solving strategy that we need to take into account certain criteria, which include the constraints. Maybe it's money, maybe it's going to be outside, maybe it's within a certain temperature, maybe it's in a certain size that we have to have it done, or a certain type of material. So, with criteria and constraint, use to develop many possible solutions to solve or satisfy human needs or wants, and to narrow down the possible solutions to one final choice. So we're looking at a situation where engineers are coming up with a possible solution to solve, or whether it's a problem, whether it's something that we need to figure out, but that design process is that systematic approach, knowing what we need to do and what I'm allowed to do, or what are my constraints to solve that problem. Now, there are a lot of different ways that you can go about learning engineering by design. One of these is through the Knoll Science Teaching Foundation. And when we go to that website, we start out with the problem. So Knowles has basically four phases in their engineering by design task. Step one is the problem. We need to define it. Now, that's one of the things that makes a difference between a scientist and an engineer. In the first sentence, if you read, it is often said that a scientist is not one who gives the right answers, but instead asks the right questions. So an engineer might be one who identifies the right problem. So once we understand what that problem is, the next part is we need to figure out the design exploration. So how do we go about in this second phase to figure out how to solve the problem? Well, we develop a potential solution. We try it out, and then we start our design optimization. What worked? What didn't work? How do I make it better? Let me go back. Let me test it out. Is what's happening here is the problem, and I start thinking with what's called a divergent thinking. So the arrows are pointing out. I'm getting broader in my thinking and how I'm trying to solve the problem. But once I get to this certain point, and now I have my solution, and now I'm starting to optimize it, now I'm diverging. So I'm focusing my thinking towards a solution. Now, one of the key things also that separates the engineers from the scientists when we're talking about this engineering by design process is the communication. How are we going through and communicating what it is that they came up with? So we don't spend a lot of time in science class, in essence, marketing what it was that we came up with. So the Knowles Science Foundation is one of the more popular ones that really focuses on engineering by design. However, they are not the only ones. In our curriculum, in our program, we use Vex Robotics. And there's a lot of different ways, even in the Vex Robotics program, when we're coding and learning how to move coding and moving the robots, that is an engineering by design process. So if we look at how Vex defines it, they have a 3-tier process. And again, if you notice, it's cyclic. Ideate. It's a combination of using your ideas and create. Okay? Then you go to implement, actually try it out, test it, and keep going back and forth. Now they have a 10-step process here where you can see understand is step 1, define the problem, explore, do the background research. You know, where you don't want to necessarily reinvent the wheel every single time, but look and investigate and see what has worked elsewhere. Define the problem, determine solutions. What are your specifications? A lot of times that's what your constraints. Ideate, start your concept solutions. Build a prototype, see how the concept works, see what you need to do with it. Choose your final concept, refine it, go back and forth, make sure it gets better. What do I need to do to improve it? Present it, get feedback from others, get approval in that case, or see what others say about it. And maybe then you need to go back and modify it again, but then actually implement the solution, test it, does it work? And again, when we go to iterate, you can see all the different steps is to do something repeatedly until a specific result is achieved. So you can go through and they go through every step with it. And I'm not going to do that with you, but you can go through and do that if you want to. Now, if you're an elementary school teacher, probably one of the most popular ways that you're going to do engineering by design, and just so you know that a lot of elementary schools are actually doing engineering by design. My daughter in her 2nd grade for her school, that was one of her specials was an engineering course. And so what they have here is what's called the EIE, which is engineering is elementary. And so this is a specific approach combining the engineering within STEM, hands-on activities, but it's used within the classroom in the elementary classroom. So you see here, ask a question, imagine a solution, plan it out. A lot of times we think planning it out means I'm going to just start building something right away. Well, no, not necessarily all the time. Planning it out could be, let's put it on paper. A lot of times now our models are computer generated programs. We build the models first before we actually build the prototype. Once we create it, we see what works, what doesn't work, we improve. And we kind of keep going again in this circular fashion. So you see, ask, imagine, plan, create, and improve. And we keep going. Now, there's a lot of common themes within these engineering design processes. One of the key ones that overlaps all of them is communicate. Define the problem and goal. Research what's happened. Look at the solutions, choose one, test it, prototype, improve it. Look at our problem and goal. What do we need to do? Do I need to do more research with it? And we keep going back and forth. But when we're all said and done, we also need to communicate the results. So again, just another example, this is from the ITEA, Standards for Technology Literacy. Define it, brainstorm, research, generate ideas. Look at the constraints. Is it cost? Is it where am I going? Is it a certain length? I mean, all these different factors come into play when we're looking at an engineering by design process. Figure out how we're going to approach it, design the proposal, make your model, test it, evaluate it using our specifications. Refine it. You want to make it better. Maybe making it better means that, oh, it's a bridge that can hold more weight. Maybe make it better means that it's a building that's going to be taller. Maybe it's going to be the car is great, but it's super expensive based upon the materials. So once we refine it and we get to the point, we make our solution and we share our results. Now, one thing that we really need to think about when we're looking at engineering by design a lot of times is we need to really think outside the box. And I want to really focus on the difference between innovation and an invention. So an invention is something that originated after a study, after experiment. This is what came up the very first time. Inventions, however, do lead to innovations. Innovation is basically an improvement to something that is already existing, whether it's a device, an object, a thing, or a process. So let's take a look at these light bulbs and bicycles. You see how over time we start with that invention. The very first light bulb is the invention. That very first bicycle, that prototype for that initial bicycle, is a new invention. But what happens with any invention is we get innovation. We look for ways to make it better, maybe more cost effective, not as expensive, better on the environment. So these later light bulbs, these later bicycles, these are all examples of innovations. Now, when we're looking at these things, one of the things that's very important to figure out is our creativity. We need to focus and harness, and we need to grow our students' creativity. So I'm going to give you two problems. Please don't look at the solution, but try to answer them first. In the problem on the left is a shovel. Think of it as maybe it's a coin on a spade, or you can think of it as toothpicks for each of the lines, and there's a quarter. You need to move two of those lines such that you have a perfect shovel still, and the quarter or the coin and the spade is no longer in the shovel. In the second one, what you need to do is you have 9 dots. You need to draw 4 straight lines that are connected. So imagine I put a pencil down and I draw 4 straight lines without ever moving the pencil up. So it's not like, oh, 1, 2, 3. I would have to lift up the pencil in order to do that. But you need to draw 4 connected straight lines that pass through all 9 dots. So I want you to pause this, think about how you could do that. Okay, so let's look at the first one. Here's our shovel, and here's our little quarter within a shovel. So what you need to do is you need to move 2 lines. Well, I'm going to take this one. So I'm going to actually have to exit out of here in order to do this. And I'm going to move this one here halfway. I'm going to take this one and move it here. So by simply moving those 2 lines, I now have my shovel, and I now have the quarter or whatever it is in the shovel no longer actually in the shovel. For the second one, for our 4-line test, you can imagine here's line 1, here's line 2, here's line 3, and here's line 4. I could do these 4 lines on a piece of paper and never lift my pencil point. Now, what a lot of you were probably doing, if you weren't able to get it right away, is that you were confining yourself into this square. I never said to stay within the square, but what we do is we mentally block ourselves. And this gets into our barriers for being creative when we're trying to come up with solutions to problems. Sometimes our barriers are perceptual, not being able to understand what it is that's going on. Emotional blocks. We have this innate fear that if it crashes, if it falls, if it breaks, if it didn't work the first time, I don't want to do it anymore. This is stupid. Or it's like, I'm afraid to put myself out there because it might not work. That's okay. Engineering and science, we don't necessarily worry about what is the exact correct answer the first time every time. There's a phrase in engineering that says fail early and fail often. Those failures help us learn. They help us learn, okay, this didn't work. Maybe why didn't it work? What do I not want to do? How do I learn from that? I think it's the Girl Scouts motto, fail, or you probably heard it elsewhere, is first attempt in learning. Failure, when we're looking at engineering, when we're looking at science, when we're looking at a lot of fields, failure is not an option. I mean, failure is not a bad thing. It's not a negative. Environmental blocks. So there might be specific biases that we have within our culture that prevent us from doing things. Intellectual and expressive blocks, understanding the tools that we're using. If I don't know how something works or what I can do with it, that's a block to my creativity. Now, I'm going to show you this following video as a strategy to enhance your creativity.
Creativity. Everyone knows that creativity is important, that advances happen through creativity, new products, new services, new ways of marketing, ways of cutting costs require creativity. But where does it come from? Sometimes we think it's some sort of natural talent which some people have and others can only envy. You're creative or you're not creative. Indeed, sometimes creative people feel that they're the only ones who can be creative. This is simply not true. Creativity is a skill which everyone can learn. It is true that some people might be better than others, just like everyone can play tennis, but some people are better than others, or skiing. Creativity is a skill. That is what we call lateral thinking. The brain forms patterns. Patterns, routine ways of doing things, routine ways of looking at things. Lateral thinking means moving across the tracks. And when you move there, in hindsight, you can see it's perfectly logical. It's based on an understanding of the brain as a pattern-making system which makes asymmetric patterns. And there are different tools which can be taught. There's challenge, where we challenge the existing concept or idea. There's concept expression, where we find the concept ways out of it. There's provocation, very powerful. We set up a provocation and we move forward from that to a new idea. Then there's random entry, where we enter at a different point. All these are logically based on the behavior of asymmetric patterns. Now that sounds complicated, but these tools are not complicated to use. Now, using just one of these tools, one afternoon, a workshop in South Africa produced 21,000 new ideas for a company. So they're very powerful. It's not a matter of just sitting around and waiting for new ideas to happen. You can actually take steps. It's like maths. You can learn maths, you can learn lateral thinking, you can learn creative thinking, and you can use and apply it deliberately. Of course, the more you practice, the better you get at it, but it's not a complex matter, and it is effective and powerful. And it goes way beyond traditional brainstorming. Traditional brainstorming is a very weak process. It's in the right direction, of course, but just by suspending judgment, that's not nearly enough. There are these formal techniques which produce, generate ideas, don't just wait for ideas to happen. So lateral thinking, as I say, is a skill. For the first time in history, we can now treat idea creativity, the ability to produce ideas, as a formal skill which can be learnt, practiced, used deliberately. And I emphasize that deliberately. It's very different from just sitting and hoping and waiting that someone somewhere has an idea. No, you can sit down and deliberately generate ideas, a large number of ideas. So lateral thinking is a usable, learnable skill.
So that is a little bit of a sales pitch on lateral thinking, but you can kind of get the idea and see how, you know, if we develop these routines in our brain, it's like if we're going down a road and there's ruts in the road, we tend to follow the ruts and we get stuck within the ruts and we don't move beyond them. Well, if we want to be creative, if we want to look at things from a different way, we need to get out of the ruts that we keep ourselves in. So constantly question, practice. We need to suspend our judgment, and it takes time. And I think one of the most important things to think about this is you need to look at this and think about these activities like a beginner. So there's a popular engineering by design activity where you're given 30 pieces of spaghetti and 30 marshmallows. And you're asked to basically create the tallest tower that you can. Now, engineers get this, and students of all ages get this activity. And what's most surprising is that the group that does best with this activity are actually kindergartners. And the reason why they do the best is because they're looking at it from a initial new perspective. They don't care if it falls down. All right, well, let's do it again. that first attempt on learning. It went down. All right, well, let's just build it again, see what worked and make it better. So they're thinking about everything for the first time. We're not, we do want to use our previous knowledge, but we don't want our previous knowledge to dictate how we move forward and what we do with things. So this is just a quick overview as to what engineering by design is. It's a lot more complicated than this. I am by no means an expert, but when you're looking at these problems and you're trying to figure out these solutions and ideas on how to solve things, it's not just the process that's important that we need to think about, but it's also how do we come up with these ideas? How do we start to think creatively when we're looking for solutions? So I hope you enjoyed and learned a little bit more about engineering by design. We're going to be doing some activities with them, and I look forward to chatting with you soon, and I'll talk to you next time. Bye-bye.